Hello and welcome to the chemistry solution. This tutorial is on electron affinity. The electron affinity is the energy change associated with an atom gaining an electron, and in most cases we're talking about a neutral atom gaining an electron. Most often electron affinities are negative values, meaning that energy is released in this process. However, there are some exceptions to this rule, where the electron affinity is a positive value. And this occurs in the case of an atom becoming very unstable upon gaining an electron. The more negative the electron affinity value, the easier it is to add an electron to a particular atom. Let's look at the electron affinity trend on the periodic table. And as I mentioned before, this trend does contain some exceptions, which we'll cover in just a second. The general trend is that as you go from the bottom to the top of the periodic table, you don't see much change in electron affinity. But as you go from left to right across the periodic table, you see the electron affinity values becoming more negative. Now let's look at some exceptions. The first exception is the noble gases. Remember that noble gases have completely filled shells, and so the addition of an electron requires that electron to reside in a higher energy shell, and this is an unfavorable reaction. And because of this, all of the noble gases have electron affinity values greater than 0. The second trend is the elements in group 2A. And the electron affinities for the elements in group 2A are more positive than the electron affinities for the elements in group 1A, even though we said that usually we see electron affinity values become more negative as we go from left to right across the periodic table. And this is because the addition of an electron requires it to reside in the previously unoccupied p subshell. So remember, as you're determining electron configurations, for each new shell, the first 2 electrons go into the s subshell. Add a third electron, that electron now has to reside in the p subshell. And the third exception is the elements in group 5A. And the electron affinities for the elements in group 5A are more positive because the addition of an electron requires it to be put into an already occupied orbital. So again, remember, as you're filling in electrons in each new shell, the first 2 electrons go into the s subshell. Then you start putting electrons into the p subshell, with the first 3 electrons going into different orbitals. But remember that p subshells only have 3 orbitals, so the addition of a 4th electron into the p orbital requires it to pair up with an electron. And the pairing of electrons requires electron-electron repulsions to be overcome. And this makes the electron affinity values for the elements in group 5A more positive than the electron affinity values for the elements in group 4A, and this is an exception to the general trend. Let's look at an example problem. Arrange these elements in order of increasing electron affinity. So from least to most negative electron affinity values: germanium, potassium, chlorine, and sulfur. Remember that in general, electron affinity values don't vary much in the vertical direction on the periodic table, but they become increasingly more negative as you move from left to right across the periodic table. So first, let's locate these elements on the periodic table. We can then see that following our general trend, potassium should have the least negative electron affinity value, followed by germanium, followed by sulfur, and concluding with chlorine, having the most negative electron affinity value in this series. Let's look at another question pertaining to electron affinity. Why does phosphorus not follow the general periodic trend for electron affinity? Remember that phosphorus is in the 5A group on the periodic table. So here I've drawn out the electron configuration for phosphorus, abbreviating the inner cell electrons with the neon core. You'll see that the 3s subshell is completely filled, and you'll see that the 3p subshell is half filled, with each orbital in the 3p subshell having 1 electron. The addition of another electron to phosphorus would require it to pair up with another electron in the 3p subshell. And in order to do that, it would have to overcome electron-electron repulsions. And this makes this process slightly less favorable than for an element in group 4a on the periodic table. Thanks for watching the chemistry solution. We hope you enjoyed this tutorial.